Hello everyone. Let's start a new project. Let's do CSIR-NET question papers. So this I'm going to solve now is June 2021. First five questions for this video. So first question, organic chemistry questions, of course. So first question here is the major project product formed in the following reaction. So you can see we have a ester, diester rather, and we are having carbonyl group, and we are putting it in presence of base. It looks very much like Claisen condensation. So basically it's like if ester is there, so on alpha carbon if there are two hydrogens. So basically it will lose two hydrogens, and basically it will lose two hydrogens and forms a bond with the aldehyde which is there. So that PHC double bond O like that, and then you get a product. You get something like this, and water is lost and you get this product. But only difference is here it's a diester. So the what happens is the other part also loses the ester part and becomes COH. This is called as Tobbe condensation. So yeah, so this is what pretty much it happens. So here it loses two protons. So here you can see here it loses two protons and this oxygen, and you get this product. That's what happens. So let us look at the mechanism. So you know this ester carbonyl group, if carbon is then the alpha hydrogen, they are acidic because if you remove this proton, you get a negative charge which is delocalized and thus it is stabilized. So what happens is now this bond comes here, this goes and attacks this aldehyde and you get negative charge. This negative charge goes and attacks the neighboring COET. So it forms 1, 2, 3, 4, 5. Now 5 membered ring is kinetically very favored. So therefore it goes and forms the bond here, 5 membered ring, and then it goes and forms like that, and then this proton again on which the aldehyde has been attacked, so that it loses this proton, and you can see here you get a negative charge. That negative charge comes back again on this, basically this negative charge is what is coming back here, and this opens up. That's how you lose the ester part from that and becomes carboxylic acid. So the answer is option B. So you need not remember the need not solve the whole mechanism during the competition. All you have to do is just look for this part, that one of the alpha hydrogen will undergo condensation reaction, one of the alpha carbon to the ester will undergo condensation reaction, so that H2O is lost, and the other part which is not alpha to the uh, whose alpha carbon is not losing the protons, so that other part will become COH. That's all. Next question. So this is bit tough question, not a bit, it's quite tough question. You have to remember all the values. So let us revise something so that we understand. So it says which of the following compound has proton NMR spectrum where you are having delta 2.4 singlet 3 proton, 3.9 singlet 3 proton, 7.25 doublet, 7.95 doublet. So we know that aromatic rings, they show peaks at very high value around 7. Okay. So here very clearly two sets of aromatic protons are there. So what happens is basically it is the concept what is called as anisotropy. So if benzene ring is there, so because of the pi electron cloud, they have their own uh, magnetic ring current. You can see it goes like that. Okay, it goes in the clockwise direction, and when you apply the magnetic field, it is aligned in this field which is already there in the magnetic field, internal magnetic field of the pi cloud of the benzene ring. Therefore it gets very deshielded because 7 is a very high value, very highly deshielded. That is because of anisotropy. So it comes at 7. Now we see that it is two sets. So what happens only when you are having para, when you are having para disubstituted benzene, you get two sets of aromatic ring, protons, because these two protons are identical chemically and these two protons are chemically identical. Okay, so these two will show as one signal and these two protons show as another signal. Okay. And now this will come as doublet because HA is different from HB, so HB will be split by HA as doublet, and HA will be split as doublet by HB. So clearly it is a para-substituted product. So all of them are para-disubstituted product. So we don't know till now which one of that is there. Now we have to look at the other thing. So what it says, you are having delta 2.4 singlet 3 proton signal, and then you are having delta 3.9 singlet 3 proton signal. So both of them are having 3 proton signal, which is singlet. So effectively 3 proton means it is generally CH3, and singlet, that means next to it we don't have any carbon containing hydrogen. So all of them actually, if you see, will fit in this, because this Me is there, beside to it is oxygen, this Me is there, next to it is oxygen. Similarly here also Me, next to is carbon which does not have hydrogen. Similarly here Me attached to oxygen. Similarly here this Me attached to this carbon which does not have any hydrogen, and same with this, same with others. So again question is very tough. So it's all about the chemical shift. So let's please understand this. If it is CH3, it is something like you are having a alkyl chain and you are having CH3. That CH3 has a peak at around 0.9 ppm. Okay, so 0.9 ppm, that's what we have to remember. Now if CH3 is attached to a carbon which is a carbonyl, so you will be adding plus 1 to it. You'll be adding plus 1 to it. So in that case, you will be getting 1.9. You'll be getting 1.9. So do we have something like this is there? Yeah. So this B is there. So this Me is attached to C double bond O. So it should come around 1.9. But we can see we are having only two values, that is 2.4 and 3.9. So definitely B is not the answer. Yeah, B is definitely removed. Then what it says is, if CH3 is attached to oxygen, so something like this is there. If something like this is there, oxygen, and then you are having CH3, and then you are having CH3, then what happens? Then this gives value of addition 2.5. It gives addition value of 2.5. So 0.9 plus 2.5, how much it becomes? 0.9 plus 2.5. So it becomes 2.4. Do we have 2.4? Yes, 2.4 is there. So what all possibilities are there? This is a possibility A. B anyway we have removed. So mostly to me it looks like it might be A. And let us look at other things also. Now if you are having ester kind of stuff, okay, something like you are having C double bond O, and O, to it is attached Me. To this is attached Me. So now what happens? Look here. Look here. Now Me is attached to oxygen. This oxygen is anyway pulling the electron, but this oxygen is more electronegative than a normal ether's oxygen. Why? Because this is getting stabilized like this. You can see here, it gets stabilized like this. So you get a kind of positive polarity, not kind of positive, you get a definite positive polarity on this oxygen, and therefore gets more deshielded. So you have to add a value of, then you have to add value of 3 to it. Then you have to add value of 3 to it. So it becomes 0.9 plus 3.0 plus 3.0. 0.9 plus 3.0, that comes to how much? 3.9. 3.9. So this looks all right to me. This looks all right to me because 3.9 as this one A, you are having this. And when M is directly attached to benzene, you have to add 1.5 to it. So what is 1.5 plus uh, 0.9? Let us see. 1.5 plus 0.9. 1.5 plus 0.9. So that is 2.4. That is 2.4. 2.4. Sorry, I had done one. This is 2.4. Sorry. Yeah. I had done one mistake. Here I added 2.5 and told it is 2.4. So it is 3.4. So 3.4 is not there. We can see here clearly we are having only 2.4 and 3.9. 3.4 is not there. So A cannot be the answer. A cannot be answered. So very clearly we are having answer as C, because let us see once again. Me 0.9 attached to ring, you have to add benzene ring, you have to add 1.5. So 1.5 plus 0.9 gives 2.4. And if Me is attached to oxygen which is attached to a carbonyl, that means ester, then you have to add 3 to it. So 3 plus 0.9, that is 3.9. Therefore these are the two values. Therefore clearly C is the answer. And for this you have to attach 2.5 to methyl, so that would have been 2.5, so it would have been 3.4. So clearly 3.4 is also not there. So the answer is option C. You can read through it. I am going slowly. You can pause also if you are not able to read. Yeah, next question. Now this is very interesting question. It says correct order of C double bond O stretching frequency in IR spectrum for the following compound is. Okay, so here you are having cyclohexanone. You are having cyclohexanone Cl axial to it. Now they have put tertiary butyl because they want to lock the ring, so that ring does not um, what is that word, uh, alter. Basically what I'm trying to say is it should not change its conformation. It should not become from like this and like that. Suddenly I forget some words. Okay, so basically it should not flip. Yeah, it should not flip. The two it should not flip. So you are locking the system by tertiary butyl. So this Cl remains axial and this Cl remains equatorial. So very clearly what happens is when you have cyclohexanone, the stronger this bond, higher will be the IR frequency. Okay, because we know it depends upon directly proportional to the bond strength and inversely proportional to the reduced mass of the two atoms bonded. So here it is carbon oxygen for all of them. So we can't talk about the reduced mass. We'll talk about the strength. So what happens is here there is no chlorine, but chlorine, withdraws electron. It withdraws electron by minus I effect. So what happens, it makes this bond stronger, so this value should be higher. So of course this will also withdraw by minus I effect, and this Cl will also withdraw by minus I effect. If both of them withdraw by minus I effect, both of them should definitely have a higher value than A. So very clearly A will have least value. So A will have least value means either B or C. Okay. Now we have to see between these two. Carbonyl, carbonyl is basically, it has two resonance structure. Carbonyl basically has two resonance structure, this and this. How much contribute? Generally it's like 25% of this contribution and 75% of this contribution in the real structure. So 25% is not less, lot of ionic character, and therefore you can see carbonyls are very electrophilic in nature, because lot of positive polarity here, and therefore nucleophile are very happy to attack here, right? So now what happens is when you are having chlorine, next to it, so what will happen if it is having plus and minus two polarities like this, plus and minus, so this minus and this lone pair, they will repel, correct? So when they repel, it will rather like to stay as C double bond O rather than single bond character, correct? So what happens because of this, when this resonance which I was talking about 75 and 25%, this will reduce further. It will not be 25%, it will be something like 15% or 10%, and that much this neutral character of the carbonyl percentage will increase. So it will be 85-90% kind of stuff. So when you are having 85-90% of stuff, so double bond definitely have a higher frequency than your single bond, and therefore this will have higher, C will have higher frequency than your B. So your answer should be C. C is highest, then B, then comes A. Right? So answer is option C. Next question. The correct match for the bond dissociation energy of CH bond of the compounds in column 1 with the values of column 2 as example of bond dissociation energy of methyl hydrogen is basically it's talking about methane. Methane is 105 kilocalories per mole. Now this is a question which is very deceptive. Easily you can get decepted, because generally we'll start thinking when you see like this hydrogen, we think that must be talking about the acidity. No, bond dissociation energy by definition means if it breaks into two radicals, that means when it is equal breaking of bond, how much energy is required. So what we are looking at, after breaking, if something is stable, that means it will be easier to break, right? So we are looking basically at the stability of, because everything is giving H dot, so that we cannot compare. We look at these dots. So we are looking pretty much at stability of these radicals. So let us see. Now this radical and this radical are, C and A radicals are stabilized by resonance, because this has gone off this proton and you're getting a radical here, and there is a pi bond, so it will of course resonate. But here resonance is between 1, 2 and 3. So this, please understand, when there is a radical, it is electron deficient in nature. So anything which is not neutral is not stable, so it is deficient. Now this deficiency is being shared by 3 atoms, so it gains kind of stability. But here this deficiency is being stabilized by 5 atoms. So of course C is more stable than your A, and C and A are definitely more stable than your B and D. So till now what we know, highest stability is for C, so it will have lowest bond dissociation energy because it is more stable, so easily to break. So rather than putting like this, I'll put it like this. So lowest bond dissociation energy, then comes your A. Benzene will not. Why it will not? Because here it was like that. The p orbitals are perpendicular and the sigma with the sigma bond of CH. So when you are getting a radical, when you remove this, the radical is orthogonal to the pi system. They are 90 degrees to each other. You appreciate this part? The radical which you have got is orthogonal to the pi system, so it cannot resonate even 0.1% also. There is absolutely no resonance whatsoever. So now what happens? This is unstable. Same is with this. So now we have to look at the carbon. Now this carbon sp2 hybridized, this is sp hybridized. So you know sp carbon is more electronegative than sp2. Why? Because sp carbon you are having 50% s character, whereas sp2 you are having 33% s character. So this has more s character. S character, you know, s orbital is closer towards the nucleus than p orbital. S orbital is spherical in shape, so it has much more penetrative effect than your p orbital. So it is closer to nucleus. That means nucleus, it will feel more attraction, so it is more electronegative. So if it is more electronegative, it is destabilizing more, because please understand, radical is electron deficient. So if it is electron deficient, it is electron deficient, that means it wants electron and you are giving more electronegative, so it is pulling away more electrons, so it is more unstable. So this will be toughest to form. So D will have highest, bond dissociation energy, and before that will come B. So the answer is CABD. Let us look at it. CABD. So it is giving you values, but basically you have to look at it. Okay, so CABD, C we said will have lowest, right? So lowest is which one? 71. Then we said CA, A will have little higher than that, so it is 90 CA. Then I said B will have little more higher, and D will have highest. So 1 is with 4, sorry, A is with 4. So let us look where is A with 4. Yeah, so looks like D to me. Then we said B is for 1, so B is for 1. Then C is for 2. C is for 2, so C is for 2, and D is for 3. So that's what it is. So the answer is option D. I will go slowly. If you want, please read it. I have written in a great detail. Okay, you can read line by line. Keep keep pausing it and keep reading it. Now this question was again very confusing, but it was very simple question. The question says the correct relationship between the following structures is that they have made it like they look like mirror images. So no, they look like mirror images. So first thing we'll think is they must be enantiomers, but enantiomer definition is not mirror image, non-superimposable mirror images. If it is superimposable, then they are identical. So if you just rotate it and you see what happens, if you rotate it, H comes this side and Me comes this side. Now this hydrogen remains exo whatever if you rotate or don't rotate, and Me remains endo. Endo means it is closer to this ring, it is down. You understand, this part is down, both of them are down, and this hydrogen. So when you rotate, you'll see that they both are same. So they both are identical. Answer is option A. That's it for today's lecture. Maybe I'll go down, you can read it. Okay, next we'll do question 6 to 10. Thank you very much.